Hello, everyone. My name is Pawan Kumar, and I am an assistant professor at IIT Hyderabad in India. So I'm pleased to present the talk, Adaptive Consensus Optimization Method for GANs. This is the work done by Sachin Santosh at IIT Hyderabad. So these are the co-authors. Here it's me, and this is Sachin and Santosh, and this is IIT. So recently, as we know, generative modeling has been at the center stage of machine learning. So for text generation, we see ChatGPT and later variants GPT-4 is creating a lot of buzz. It solves wide variety of problems, reasoning and writing poetry and so on. And previously we had BERT and Chinchilla and PAM and so on. And similarly for image generation, some new developments have happened in past 2-3 years. For instance, DALI 2 from OpenAI is a image generative model, and then we have ImageGen from Google, and we have other variants like GAN and very recently GigaGAN and so on. Generative modeling has a lot of applications, and this is the reason why it's at the center stage right now. Just to list some of the important applications. For instance, let's say it's useful in data generation and augmentation. So in medical domain, data is very scarce. So for instance, let's say MRI images, the data is really scarce. And if you want to build a classifier to say that the MRI scan has some issue or not, to identify the issue and so on, then you need to build a classifier. But then since the data is scarce, the classifier may not learn that well. So hence, in this case, we would like to have a data augmentation and then build the classifier on that. It could be used for representation learning. So basically, and then later on for downstream tasks, for instance, anomaly detection, data compression, and clustering. Obviously, generative models have now many creative applications. For instance, in art, it can generate some new art forms. It can create some new designs, for instance, new bedroom design, new, let's say, restaurant design, or it could be used in entertainment in many ways for image processing, video processing, and then it could be also used for image generation. So if we focus on GAN, which is one type of generative model, there are like other 3 or 4 types. For instance, diffusion models have been very popular recently. And then we have autoregressive based models also, normalizing flow based model and so on. And GANs for the past several years have been one of the key generative models. And it is still very relevant. Okay, so especially with some of the new papers claiming they are as good as diffusion models, also in text to image generation. Okay, so so when we train GANs, there are certain issues also. For the images that are generated, understanding the quality of these images, metric for that, and all this are still an open problem. So one of the most difficult problem in GAN that people face is mode collapse. So basically, this is this is an issue where the generator fails to kind of create diversity in the data generator. For instance, if there are handwritten digits, then it starts generating only few of the digits. Okay, so basically it loses out in diversity. And there is also an issue of training instability. So GAN's training can be really unstable, especially in the beginning. It's essentially boils down to min-max problems. And those are usually very unstable. Okay, so and as I said, evaluation metric can also be an issue. So for instance, if you're generating some images, then how do you know that these images that are generated are are good one, right? Because these are new images generated, so it's difficult to know how to evaluate the generation quality. So however, we will see later that for certain data sets, people have worked around and found some metric. And GANs usually tend to have very high computational requirements. If you're running on let's say 1 or 2 GPUs, then for you may have to run perhaps for a week as well to train on some data sets of high resolution. Okay, so and there again essentially involves two architectures, generator and discriminator. They are both neural networks. If you're working with images, they are usually convolutional networks, and they come with their own hyperparameter. As we know, there are learning rates, batch sizes, architecture choices, regularization techniques, and so on. So all this makes GANs really difficult to train. Okay, and the focus of this work is on the training. Okay, the efficient training. Again, basically, we want to propose a solver which can solve this min-max optimization problem really well. So this is the min-max problem I'm talking about. On abstract level, this is a min-max problem with where we want to do a minimization over the generator parameters, and then we want to do maximization over the discriminator parameter. So so in this work, we propose a new optimization method, which we call it adaptive consensus optimization, and it is integrated with the accelerators like RMS-prop and ADAM. So apparently, momentum still is required. Okay, which other papers also exploit. So what we have is that the proposed method is fastest to train among the second-order methods, and extensive experiments have been done on 5 of the most popular data sets. And we have shown a complete convergence analysis for our method with RMS-prop. And so basically what we did is we identified the fixed point iteration behind this, the proposed method, and we saw that the necessary conditions for the convergence of the proposed method is satisfied. And our analysis is unified one in the sense that it's not just the analysis for the second order method, but it's the second order method with the momentum. And this we believe is done for the first time. And this is the algorithm. I won't go into the details of the derivation, but I will just go you and let you through some through the algorithmic steps. So we run a for loop. Basically, we are supposed to solve the min problem and the max problem. And we run this for loop over t, and then we compute the first derivative, and then we compute the second derivative, but we multiply that with delta x, which is the difference of xt and xt minus 1. And then we compute dxt here, which is this dxx is a matrix, and then delta x is a vector. So overall, it's a vector, and then we add it with a vector here, and then and here we compute the momentum vector mxt, which is a average of the previous mt minus 1, and then the dxt that we computed in the 5th step. And then we compute the velocity vector as follows, and we scale the mxt vector, and then we also scale the velocity vector. And then similarly, we do these steps for the y. And then once we have done that, then we do the x update as follows. So the m hat xt that we computed here at step 8, and then vxt vector that we computed at step 9. So we do this update using those, and then we also do this update similarly for y vector. And these are the parameters we have, like learning rate, and then the decay terms that we choose. These are hyperparameters. And then m0 we initialize to be 0, velocity vector, the initial one, we take it to be 0, and t0 is the initial step. So this is the algorithm. And let us look at the results. So if we look into the MNIST data sets, then then this is our method. So it tends to produce images that are close to the original, and these are also compared with other second order method like ACGD. If we look into fashion MNIST as well, we have similar outputs here, which tends to correspond to the original image as well, and it also tends to create good enough diversity. And here we compare CFAR data sets. So in CFAR data set, we can see, so these are the generated ones and these are the original one. CFAR data set tends to be a bit challenging. Here our method matches with state-of-the-art ACGD method. Now, and here we have finally on FFHQ dataset. So datasets which have less complicated features, for instance, faces, then these methods tend to do okay. So here most of the features of the faces are captured very nicely. And here we also do an Inception score plot valid for CFAR10 datasets, and we see that our method compares well with the ACGD method, which is a second order method. Now, our method is a second order method, but we see that it's much faster than the existing second order method. So this is the blue one here, and this is just above the first order method ADAM. So this was a small data set, so the differences look very small. So we also compare the time plots for the large data sets. And for large data set, we see that, that this blue curve, which is our method, is much faster than CONOPT, okay? And if we look at the scale, CONOPT was somewhere here. This is the red one, okay, above the blue one, right? And then this is the CGD method, which is the state-of-the-art second order method. So this is like most costly method. Okay, so it was so costly that on large data set we did not even compare it here. It took a lot of time. So from this we see that like our method is the fastest second order method with state-of-the-art generation quality. So just a quick remark on the convergence of the proposed method. So as I said, we do a full-scale analysis with RMS prop. So these are the complicated steps that look like are the RMS prop combined with the second order updates that we do. And so this is the fixed point iteration we look at. And then if we look at the derivative of that fixed point iteration, then it could be written as I plus HA. And for good enough H, and if A happens to have eigenvalue within the unit ball, then the fixed point iteration theory tells us that it will be a convergent method, and this is what we prove this in the paper. So with this, I thank you for your attention.